On March 28, 2022, a line of snow squalls tracked across southeastern Pennsylvania. On that day, the National Weather Service issued 15 snow squall warnings, warning the public about the sudden onset whiteout conditions. But they missed one key place: this stretch of I-81 going through Pottsville, Pennsylvania. Drivers on I-81 drove straight into whiteout conditions, leading to a 50-car pileup and the death of 3 people. This oversight that ultimately closed the northbound side of I-81 was because of this: a radar gap in coverage between 3 radar sites: State College, Pennsylvania, Binghamton, New York, and Mount Holly, New Jersey. The National Weather Service was missing one of their key tools when issuing sudden onset weather warning, and it cost lives. The story on I-81 is not uncommon. This radar gap is one of dozens in the United States, where federal radars are too far away to provide meaningful coverage. Across the United States, there are 143 radar sites covering the contiguous United States and 16 covering Alaska, Hawaii, and other U.S. territories and military bases. Between these 159 radar sites, 94% of the population and 73% of the United States' landmass is covered. And these radar sites and this coverage is dependent on one key type of technology: Doppler radar. You might recognize the name Doppler from the phenomenon known as the Doppler effect. Christian Doppler figured out that if an observer is moving relative to a wave, there will be a change in the frequency of the wave. And you've probably experienced the Doppler effect when a train is passing by you. From afar, the sound of the train is pretty low, and as the train gets closer, the pitch of the train gets higher. Well, the same idea can be applied to getting 2 key pieces of weather data: reflectivity and velocity. Doppler radars work by sending out quick radio wave pulses into the atmosphere and wait to see if they get any bounce back or return signal. Once a return signal is registered and sent to the corresponding computer system, we learn 3 quick things in succession. 1, how far the target is from the radar. 2, how fast the target is moving and in what direction. 3, how strong the target is. These 3 elements, distance, reflectivity, and velocity, give us maps like these that you've probably seen before. With Doppler radar, meteorologists are able to visualize wind patterns and precipitation. And with the installation of dual polarization radars in 2012, the Doppler radar system can now give us an understanding of not only the strength of precipitation, but the type of precipitation, including the size of hail or type of snow. But here's the problem: these radio waves can only go so far before their return signal isn't helpful anymore. And in the United States, these federally installed radars have an optimal range of 71 miles. And one city, sitting right outside that range, 80 miles away from its closest radar, is Charlotte, North Carolina. The Charlotte region is one of the largest metropolitan areas in the United States not covered by radar. And this area is home to millions of people. On January 9th, 2024, an EF1 tornado touched down in Claremont, North Carolina. With the closest radar site over 80 miles away from Claremont, meteorologists at the Greenville-Spartanburg National Weather Service office barely saw the storm on the radar, let alone had enough information to issue a warning. And that's because the further away you get from the radar, the worse the resolution is. This EF1 tornado ultimately injured 4 people and killed 1 person. The reason Charlotte and many other places in the United States don't have adequate radar coverage is because of how meteorologists read the atmosphere to predict storms. The quality of radar coverage is based on a metric called the beam height above ground level. Basically, how high is the radio wave signal from the surface of the Earth? So Doppler radars send out radio waves at a very slight angle. One key reason is to avoid buildings, trees, other natural features. But the other more obvious reason is that the weather that needs to be warned is developing well above our heads. And this is where radar beam tilt comes in. Doppler radars across the United States are set to read at 0.5 degrees above the horizontal, a small enough tilt that over miles, radar beams can slice through the atmosphere to get an accurate reading of the clouds above us. And the curvature of the Earth makes this slice even more egregious. Closer to the radar site, Doppler radars can see storms in high resolution, getting strong return signals from their radio waves. But as that radio wave travels further from the radar, not only does it get higher in the atmosphere, reading parts of the storms that might not impact us on Earth, but also the return signal gets weaker, leading to a worse resolution on radar.
Okay, I realized that what I just said, I don't like how I described that, so let's try it again. Basically, the further you get from the radar, the more area that radio wave is going to be covering. You can think of it like holding a flashlight. Close to the flashlight, the circle of light or the beam of light is going to be relatively small and well-defined. But the further you get away from the physical flashlight, the more fuzzy that circle of light is going to get and the wider that beam is going to propagate. So that's how we can think of those radio waves propagating through the atmosphere. Close to the radar site, they only have a little bit of atmosphere they need to cover. But the further away they get, the more atmosphere they need to cover, and therefore the worse resolution in terms of radar reading.
Such that 55 miles from the radar site, you're getting readings at 4,000 feet, whereas at 150 miles from the radar site, that beam is cutting through the clouds at 18,000 feet. And here lies the key problem in radar gaps. The further we get from a radar site, the higher into the atmosphere we're reading and the worse resolution we're getting, which means predicting suddenly developing storms becomes increasingly difficult. And that's the exact problem the meteorologists at the Greenville-Spartanburg National Weather Service office had on January 9th, 2024. But if radar gaps are a known problem, then why do severe weather events continue to go unwarned? The United States has one of the most comprehensive and advanced weather radar systems in the world. The radar system covering the United States is known as NEXRAD, which stands for Next Generation Radar. It was installed across the United States in the 1980s. In 2017, under the Weather Research and Forecasting Act, Congress asked NOAA and the Department of Commerce to address and evaluate the gaps of NEXRAD. The report, published in 2020, found that since the implementation of NEXRAD in the 1980s, the National Weather Service has made huge strides in advanced warnings. Tornado warnings have gone up from 4 minutes in the 1980s to 11 minutes in the 2010s. And flash flood warnings have gone up from 18 minutes in the 80s to 70 minutes today. Undoubtedly, data from NEXRAD has saved thousands of lives. But radars are expensive to maintain and even more expensive to install. And ultimately, the report concluded that there is not a negative impact to warning performance tied directly to radar coverage. This report argues that at the end of the day, it's not radars who issue warnings, but meteorologists. The results of this report were met with criticism from meteorologists in academia and the private sector. Yes, meteorologists issue warnings, but more granular and raw data will and would help bring more accurate warnings to more people. So with no expected changes at the federal level, local municipalities and communities are working to address these radar gaps themselves. First, communities are already working to fill in the gaps by tapping into smaller, more localized radars, utilizing radars at airports or universities. In Charlotte, the Weather Service relies heavily on the FAA radar installed at the Charlotte Douglas International Airport. And universities, such as the University of Missouri and Western Illinois University, have recently installed radars on their campus to provide additional coverage. Second, communities are implementing an initiative called Lower the Beam, bringing their radar beam tilts down from 0.5 degrees to 0.3 degrees. In Baton Rouge, Louisiana, the KLIX radar has been tilted down, adding huge swaths of enhanced coverage to central Louisiana. Over the past 10 years, the National Weather Service has lowered the beam at 24 radar sites. Third, for where places where installing or maintaining a radar is cost prohibitive, there's a new industry emerging known as radar as a service. Climavision, a weather tech startup, has been the leader in this new emerging industry. And their business pitch is that we'll maintain the radar, you pay for accessing the data. Since August 2022, Climavision has installed 24 radar sites across the United States. These new privately owned radars allow TV stations and local governments to get radar data without having to maintain a site themselves. And finally, numerical weather prediction continues to improve, allowing the National Weather Service and Storm Prediction Center to issue more detailed watches ahead of severe weather days. Radar gaps have serious life-threatening consequences. While communities are making efforts to mitigate these gaps, radar gaps still pose an enormous threat to hundreds of thousands of people living across the United States. Improving radar coverage is a complex task that requires innovation and collaboration between federal and local agencies and the private sector. It's critical that we continue striving to address these gaps and instill the best possible warning systems for communities across the country. Thank you so much for watching this video, and if you have any suggestions for topics that I should cover, leave them down in the comments below.